Okay, in this video I'm going to be explaining a little bit of the basics of the wind tunnel and airfoil theory in general. So basically we have a pretty simple wind tunnel here. Basically at this end over here it's sort of a bell shape part of the body of the wind tunnel. Basically it collects the wind and then it sends it into a test section where an airfoil is. That airfoil is hooked up to various devices that allow us to get different properties of the airfoil as air is going over it. And then back here we have the fan. The fan is a suction fan, so it sucks air through here. It doesn't blow air onto the fan, let's say, like you might think. The reason for that is the air coming off of these turbine blades are actually going to cause a lot of turbulence, so you actually get a lot smoother air if you have a suction turbine like this. Okay, so basically what we're going to be observing is the lift and drag of an airfoil. Okay, so the airfoil that we have is the NACA 0012. It's largely shaped like this. This is a airfoil code. It wasn't the 12th one they made. But basically the numbers mean certain characteristics about it. So basically the first two numbers have to do with its camber. So the camber is the mid-plane curve. So basically if you were to split it sort of in half, basically this line here would follow the curve if there were a general curve of the airfoil. Certain airfoils are very, very curved. Other airfoils, like this one, is symmetrical. So basically, when the first two numbers are 0, you know you have a symmetrical airfoil. And then the 1, 2 back here has to do with its thickness and the position of its maximum thickness point. But basically, all you need to know is it's a symmetrical airfoil, and it creates lift if you vary the angle of attack, and drag as well all the time. So yeah, basically you have the airflow coming over this way. There's an inherent force that is trying to pull the airfoil back, and there's an inherent force that tries to move the airfoil up or down. In this case, since the leading edge of the airfoil, which is this guy, is facing downward and the trailing edge is up, it's actually going to create lift in the downward direction. Now I know if you had an airplane wing that had a negative angle of attack, it wouldn't get off the ground, right? This is correct. The reason we are using a downward angle of attack is because the instruments on the wind tunnel seem to work a lot better when the forces are put on it in this way. So that's why. And additionally, there are applications such as race cars and other racing machines like that rely on upside down airfoils to actually keep them planted on the ground. So it is valid for tests of that nature. So anyway, the drag is sort of easy to get. Basically, as the air is flowing over the surface, there's friction over that surface, right? You have shearing forces, that's what we call that, and it slows the airfoil down. But it's a little bit different when it comes to the lift. The lift is actually due to a difference in pressure over the top and bottom of the airfoil. So effectively, what you have here is on the bottom of the airfoil, so this airfoil is at an angle of attack, a slight angle of attack alpha. Basically, as it's going under the bottom here, the airflow is getting pinched. And right in that section there, as that airflow is getting pinched, it's actually increasing in velocity. When you increase in velocity, you actually go down in pressure. Okay, now if we look at what's going on at the top half of the airfoil, basically this air here is hitting it's not quite a wall, but effectively it's going to be slowed down by the increase here. So basically, yeah, it'll look like it'll collide it for a little bit, but it's actually colliding so much that it's slowing these particles down. Where here you have a slight gradual increase, slight gradual decrease in the sort of area of flow that the air is going through. So basically, in that high-speed section here, you're actually creating a low pressure, but since it's going over the top here, it's actually slowing down the airflow, causing a high pressure. So basically, that difference in pressure creates lift either up or down. In this case, we have the low pressure on the bottom and the high on top. So that high is going to be pushing down on that low and creating negative lift. So effectively, it's important to note that the backside of the low pressure side of the airfoil is more beneficial in terms of lift. Okay, so let's say you had an airfoil here. This is at an angle of attack. It's sort of angled like that. It's creating lift in the downward direction. But let's say you had an airfoil, same exact airfoil here, but you had a much steeper angle of attack. So you have something like this, a much steeper angle of attack like that. Okay, the airflow would certainly come in like this. Okay, it hit the surface, it either go up over the top. Okay, it's going to be slowed down very severely since it's at such a sharp angle of attack, or it'll go around the bottom like this. Okay, now at lower angles of attack, the airflow is able to stay attached along the back side of the airfoil. But at higher angles of attack like this, it's detached, which means there's a lot of turbulence that's swirling around behind the airfoil there. That is no good. So basically you lose all the benefit you have of this low pressure system gained by this converging section of air. Yeah, even though you have an increase in high pressure over here, since you're losing all the low pressure down there, you actually lose a lot of lift. So as you increase the angle of attack, the lift will also increase to a point called the stall angle. And when it's past that stall angle, you have a lot of turbulence behind it and you have detached airflow from the surface of the airfoil. So I know that's kind of a lot to get your head around, but effectively what we're going to do in this lab is we're going to angle the airfoil, we're going to get the drag force, the lift force, and we're going to see where the stall angle is, meaning where it becomes turbulent behind the airfoil. In the next video, I'll explain a little bit more about the nuances of the wind tunnel itself.